This video covers fluid dynamics, flow rate, and Bernoulli's principle. Up until now, all the fluids that we've discussed, both liquids and gases, have been static, meaning that they were not moving. Today we're going to talk about fluids that are moving, meaning they are dynamic. They have a flow. In physics, we like to simplify everything to the easiest, most ideal situations so that we can study them a little bit easier than looking all the complicated ways that they can actually act. So for this section, we're going to make a couple of assumptions. We're going to assume that the flow of this fluid is steady, meaning that the flow patterns are maintained without turbulence, that the fluid is incompressible, meaning that its density is constant all the way through, that the fluid is non-viscous. This means that there is no resistance to the flow, and that the flow is irrotational. What that means is there are no swirls or eddies. So with all these assumptions, what we get is a streamline. So this picture down here, all these blue lines show a stream that one particle of water, in this case, would travel as it moves through these pipes. The first equation we're going to look at is the continuity equation. Now, what we have listed down here is not necessarily the equation we're going to be using, but it's derived from these variables. So the continuity equation tells us that an incompressible fluid, like the ideal fluid we're looking at here, as it flows through a tube with different cross-sectional areas, which means that at this point we have a very large area, and then at this point we have a smaller area, and then over at here we have a larger area. So as this fluid goes through these different areas, the rate at which mass flows past any point in the tube is constant. So if this was not true, if the flow rate varied, the fluid would build up at points where the flow rate is lowest. So if our mass flow rate is constant all the way through, then using these variables, we can derive a new equation for continuity, which is rho times area times velocity. So this is true at all points. So let's say we're looking at these 2 points. Here at this first point, we have a very large area. Over here at this other point, we have a smaller area. So if our mass flow rate is going to be constant, that means we have to have a small velocity at one point where we have our large area, and then increase our velocity when we have a smaller area. Now, our original equation include rho, but we can assume that the density is staying the same in both of these places, so that density variable can cancel out. And so all we're left with is area 1 times velocity 1 is equal to area 2 times velocity 2. Now for these, for the most part, you're going to be dealing with circular areas, so a good equation to also memorize is pi r squared. Now the very important thing is a lot of the times you're going to see these kinds of problems in the multiple choice section. So they're going to ask, what happens if I increase my radius by 4? Well, because my radius is being squared, if I increase the radius by 4, or if I double it, in this case, if I increase it by 4, I'm actually increasing my area by 16. So if my area increases by 16, then my velocity has to decrease by 16. And so what I'm saying here is that we're going from a small area to a large area. And so my velocity should be very large at this point, and then it should become smaller by a factor of 16 when we come to the larger area. You can relate this to the water coming out of a hose. You know from experience that if you reduce the area at the end of the hose, you know that the water comes out faster. So that's a direct relationship of this continuity equation. Another equation very important to this section is Bernoulli's equation. Now, this equation comes from conservation of energy being applied to fluids. So what this says is that our pressure plus our rho g y, you can see that this equation is very similar to gravitational potential energy, plus 1/2 rho v squared, again you can see that this is very similar to kinetic energy, is going to be constant. So this is true at the beginning, this is also true at the end. So remember, you're applying a conservation of energy essentially when you use Bernoulli's equation. Now, if you look at this equation, it says that if the velocity were to increase, in order for us to stay constant, something else has to decrease. If we're looking at point 1 and point 2, the y's will be the same. So this is not necessarily changing. So the only other thing that can change is my pressure. That means if my velocity goes up, my pressure has to go down. Now, this is opposite of what you would expect. When a hose shoots fast moving water at you, it hurts, and you interpret this as a greater pressure, not less. But the pressure that we're talking about here is the pressure in the fluid between the molecules of the fluid. Another way to think about this is if you're in a traffic jam, it is very tight and slow, and the pressure between cars is high. However, when you pick up speed, the flow seems smoother and there is less pressure. So if my velocity increases because my area decreased, I'm also going to have a decrease in pressure. This picture is simply showing a summary of Bernoulli's equation. Remember, if we're applying conservation of energy in this case, then what we have at the beginning should be equal to what we have at the end. Now, a good way to memorize this equation is relating it to potential energy and kinetic energy. And because we are dealing with pressures, adding pressures to the beginning and to the end as well. So here, these H's are actually going to be measured from some low level like we did in regular energy problems. So we're going to decide on a reference level and measure our H's from that point. In this first example, we have a pipe with position 1 and position 2 labeled. Now, here we can see that the area is going to be the same at point 1 and point 2. Normally, these types of problems ask you to solve for the pressure at these different points, or the different heights, depending on the information given. So here, let's assume we're going to be asked to solve for the pressure at point 2. Now, because the area at point 1 is equal to the area at point 2, that means our velocities must also be the same. So if we apply Bernoulli's equation, this first section and this section are automatically going to cancel out because the velocities are going to be the same in both parts. Now again, you want to think of rho g y as gravitational potential energy. So here we need to choose a reference level. Again, any reference level that you choose is fine as long as you're consistent all the way through. But the easiest thing would be to choose P1 as your lowest level. Now, this is a little bit different from how we treated height in previous pressure problems. When we saw the absolute pressure equation, it was P is equal to P naught plus rho g h. And h had to do with depth. Well, here, this y is going to be the height above our reference level. So if we're calling this red dotted line our reference level, then y1 will be 0, and y2 will be this distance from here to our reference level. Now, if we rearrange our equation, right now we have P1 is equal to P2 plus rho g y2. If we rearrange this to solve for P2, we get P1 minus rho g y2 is equal to P2. Now, if we had numbers, we could plug them in at this point, but we can look at this a little bit conceptually at first. We can see here that we have some pressure, and we're going to subtract another pressure depending on our distance y. So that means that as long as y2 is a value, P2 will be less than P1. So we can say that our pressure is going to decrease from point 1 to point 2. In this example, we see a small pipe going into a larger pipe, and so we can assume that there's a fluid flowing through here. At position 1, we have a diameter labeled. At position 2, we have 2 times the diameter labeled. At position 1, we have 4 meters per second. At position 2, we don't know the velocity at that point, so we're trying to solve for it. At position 1, we are given our pressure in atmospheres, but we know that pressure has to be in pascals, so we can turn that into 2 times 10 to the 5th pascals for our pressure 1. And we're also asked to solve for pressure 2. So one of the first things you can do is solve for our velocity. We know because of the continuity equation that area 1 times velocity 1 is going to be equal to area 2 times velocity 2. Over here, I've written our equation for area, but instead of radius, I've put diameter so we can see how our diameters affect our areas. And again, I want to solve for our velocity 2. So I'm going to rearrange this equation as A1 V1 over A2 equals V2. Our area 1 is going to be pi d divided by 2 squared times V1. And my area 2 is going to be pi divided by 2d divided by 2 squared. And this relationship will give me velocity 2. So I can see that the pi's will cancel out. The 2's inside this parentheses will cancel out. And so the top part becomes d squared divided by 2. Actually, that's 4. Times velocity 1 divided by d squared. Again, you can see that those diameters will cancel out as well. And you're left with V1 divided by 4 is equal to V2. So if V1 is 4, and we divide that by 4, then our velocity at position 2 is simply 1 meters per second. This makes sense because we have an increase in area. So if we have an increase in area, we should have a decrease in velocity. Now let's go back and try to solve for our pressure at position 2. Now, because we are looking at this conservation of energy equation, we want to choose a reference level. Again, the easiest thing would be to choose the lowest point. In this case, it's right through both position 1 and position 2. That means we can disregard these H1 and H2, Y1 and Y2. So our equation now looks like P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. By this point, we've already solved for our velocity 2. So the only thing we don't know in the entire equation is pressure. So we can simply solve for pressure. That becomes P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared is equal to P2. This simplifies down to 1/2 rho V1 squared minus V2 squared. It's important that you notice here you cannot factor out that squared. You have to leave V1 squared minus V2 squared. And then we can plug in all of our numbers and solve for our pressure. When you plug in all of your numbers, you should get a value of 207,500, and this is in pascals. Here I assumed that my fluid was water, and remember that the density of water is simply 1,000 kilograms per meters cubed. Our last example has to do with a giant container of water, in this case, that has a small opening down at the bottom. So here I've labeled two different positions, position 1, which is at the top of the water, and position 2, which is at the bottom where this little opening lies, and here we're going to have water coming out. And so usually you're asked to solve for your velocity of the water as it comes out of your little opening down at the bottom. Now, for these types of problems, you're going to be making a couple of assumptions. Here at position 1, our water is being exposed to the air, so the pressure is going to be equal to atmospheric pressure, which is 1 times 10 to the 5th pascals. And position 2, because we're considering the point right outside of this little opening, we're going to say that the pressure that it also experiences is 1 times 10 to the 5th. It's also atmospheric pressure. So again, these assumptions will always be true. If you're considering the point right at that opening, then the pressure will also be atmospheric pressure. Another assumption we're going to make is if we look at position 1 and we compare it to position 2, the areas are very, very different. So at position 2, we have a very small area. So we're going to have a very large velocity. And on the other hand, at position 1, we have a very large opening and we have a very small V1. So for all intents and purposes, this V1 is going to be approximately 0. And so again, for these types of problems, that's an assumption you're always going to make. So again, before we get started, let's set a reference level. Again, the easiest thing would be to put our reference level right through one of our points, which in this case would be position 2. That means that position 2 has no y value. We can also do a couple of other eliminations. At the beginning, our velocity 1 will also be 0, so this entire piece goes away. Because our pressures are going to be the same at position 1 and position 2, then these two components also go away. So all we're left with is rho g y1 is equal to 1/2 rho v2 squared. And if you notice, this is identical to a conservation of energy problem, or it looks very identical to a conservation of energy problem. You have your potential energy at the beginning is equal to your kinetic energy down at the bottom. Again, the important thing to remember here is that we do have an opening on both sides, so the atmospheric pressure is what's affecting both of these open-ended pieces. So if we're trying to solve for our velocity, our rho's will cancel out. So again, it didn't really matter that we were dealing with water because our densities did not matter. And rearrange this to get 2 times g times y1 times the square root, and take the square root of that entire value, is equal to v2. Again, it's always important to deal with equations before you start putting in your numbers so that you can get practice with those first.